Because we're using equine blood for today's demonstration, our horse wasn't well hydrated when he was our donor. We got about 9.5 cc's of prepared PRP out of a 20 cc blood draw. When you're working with a human that's properly hydrated, this will typically yield about 10 to 12 cc's of PRP. You can see now that we have our PRP drawn into individually capped 1 cc syringes. We're going to place these into the heating element of the bioincubator. The heating element of the bioincubator is located in the front, and you can notice the difference between it and the cooling element due to the nylon insulator. The nylon insulator and ceramic core heater is actually part of the patent pending technology that makes this device unique to Juventix Regenerative Medical and superior to other knockoff or not true bioincubation processes such as aluminum dry block heaters. The process of using a ceramic heater allows even distribution of the temperature as well as rapid heating and cooling. Anyone who knows about cars or car modification know that you would want to change from your aluminum headers to ceramic headers because they will cool off more quickly without expanding or breaking. The same thermodynamics hold true in the bioincubation process. By using a ceramic heater that's coiled around each of these inlets, we're able to evenly distribute the heat. By passing that through a nylon insulant, we're able to reduce any direct contact of the heat to the platelets, which keeps this from denaturing the platelets. It's also been shown to increase the production of fibrinogen, which is going to give you a more dense platelet-rich fibrin that is also more flowable and will work more appropriately as a cellular scaffolding, whether being utilized in aesthetic applications such as dermal filler, in wound care, filling the defect of non-healing ulcerative wounds, or in orthopedic and other applications. So now we're going to take these individual 1 cc syringes that have been capped and place them into the bioincubator as seen here. We're going to repeat this process until all of the syringes have been placed safely into the bioincubator. The bioincubator has 8 tube holders that will fit from 1 to 3 cc syringes, as well as 2 larger format tube holders suitable for up to 5 cc syringes, which will most commonly be utilized in orthopedic applications. The smaller your syringe, the less resistance you will have upon administration, which makes it more appropriate for dermal applications to reduce bruising and patient discomfort. Once your syringes are placed in the heating element of the bioincubator, you're going to hit the start-stop button on the right-hand side of the machine, notated by the thermometer heating element. This is now going to expose these syringes to 55 degrees centigrade indirect heat for 12 minutes. This is going to increase the excretion of calcium from the platelets, which is going to trigger the thrombotic cascade. That's going to cause the platelets to turn into what's called platelet-rich fibrin matrix. This is going to provide a cellular scaffolding as well as be anti-inflammatory in properties from the excretion of components such as beta endorphin that are enhanced through this process. What bioincubation is doing at a cellular and scientific level is speeding up the metabolism of the platelets through exciting mitochondrial function through the application of heat. That triggers the expression of calcium, which then triggers the thrombotic cascade. And you'll see we put in liquid PRP. When this is done with incubation, you're going to see a fibrin gel matrix. After incubation, these syringes are going to be moved to a cooling element for 4 minutes. The cooling element is to slow down excitation of those platelets and mitochondria to stop the thrombotic cascade from continuing. This is going to give us a flowable product that is stable for hours. Unlike traditional historic activation methods such as calcium chloride, CaCl, or the utilization of hormones such as bovine thrombin. While those methods of activation are older, they've been shown to be less effective due to stressing the platelets, which causes the excretion of different growth factors, which can be pro-inflammatory and actually cause pain and discomfort in the patient, as well as exceeding FDA minimal manipulation and homologous use guidelines. The Juventix bioincubator allows you to prepare platelet-rich fibrin matrix in an FDA-compliant fashion. Now that the heating component of the plasma bioincubation process is complete, we're going to move the syringes back to the cooling element, as you can see here. Taking a pause, we can see that our clear PRP has now become opaque, representing the higher density and molecular weight of the platelet-rich fibrin matrix gel. After the syringes have been moved to the cooling mechanism, we're going to press start on the cooling section, which is notated by the fan icon. This will air cool these samples for 4 minutes to slow down the thrombotic cascade, resulting in a more stable and flowable platelet-rich fibrin matrix gel.